Hello everyone, welcome back to class 6 power system. So as you know that in last class we talked about power system transformers, and transformers, as you have seen that in the last video, transformer has winding resistance and inductance, as well as core resistance and inductance. So in this lecture we're gonna see how can I find those parameters, as well as how to put together transformer coils to make three-phase transformers. So let's see here. So as you remember from the last lecture, that transformer has a core, and core is there to produce flux, and that core also has inductor and the resistor in parallel. So how to find it? If you remember last lecture, if you remember that it has, if we referred everything to the primary, right? So that's the core over here. Then you have, so that's your V2 prime. This is your R equivalent 1 plus JXE1 here. And this is your core XM1 J, and then RC1 core resistance. And this is your V1, right? So now, our goal is to find those all resistance and inductance in the transformer. To find this one here, we do a open circuit test. That means your load is open. That means your load is disconnected here, okay? So that means what you have here is disconnected. That means there's no current here, right? Current is zero here. So I2 prime is zero. So that means only current is here. If this current is zero, then this branch is not existence, okay? So that means we have only this part. You have only this part here that is right here, this open circuit test. So open circuit test is done to find the core parameters, okay? So core parameters, iron loss, all right? And also to do that, what are you gonna do? Now we're gonna apply a voltage to the primary, and we're gonna watch for the rated voltage. We're gonna apply a rated voltage to the primary and see what's current going there. So on doing that, we also have measure power, how much power you supplying. So is power, that's power is lost here in the resistance. So then also the voltage and current. We have the reading for IO, reading for V1, reading for the power. So how do you find these two parameters? That's what we're trying to find, right? So if we know power, if we know voltage, we can easily find RC1 using this equation over here. So V1 squared over P0, right? So that's the equation for to find RC1. That equation came from basically this one here. Your P is V squared by R, right? We can modify this equation to find the resistance over here, right? So that's the resistance one, right? So once you have the resistance, you can easily find IC. So let's IC going to the resistance would be V1 over RC1, right? So they have the resistance now. So now this IC, IM, and IO, they're in related in kind of vector form. So IO is basically IC plus J IM. So to find the IM now, your IM would be, let me treat this. I0 would be here IC squared plus IM squared, right? So then to find the IM, you can basically do I0 squared minus IC squared, right? So you can find IM now. Once you find IM, you can find XM1, that is basically V1 over IM. So now your goal was to find these two, XM1 and RC1. You already found that, so that's the two parameters you know. Once you know XM1, you can easily find L. L would be what? The magnitude would be L would be x m over omega. That's the magnitude of L, right? So that's your omega is 2 pi f, you know that. So if x m would be 2 pi f, that's, you can find the value of L from there. All right. Again, this is done in open circuit. For the open circuit, you're applying the rated voltage in the primary and watching for the current I0 and also measuring the power P0. And to measure the winding parameters right here, we're going to short circuit. That means your secondary is now short circuited. Once secondary is short circuited, you apply a voltage until you get the rated current. You don't want to apply rated voltage. If you apply rated voltage, current would be so high that it's gonna destroy your winding. So you apply a voltage until you get to the rated current. So ISC over here is I rated, right? And you also find PSC from the supply end. So once you have that, you can easily find ZE1, E1 whole impedance over here by using IBSC over ISC. This is the magnitude, all right? So then also you can find RE1 by using this equation over here, PSC over ISC squared, right? So this again, this is all magnitude, right? So once you have RE1 and G1, you can find again GE1. If you look at here, that GE1, if you try to find a magnitude, that would be what, RE1 squared plus XE1 squared. So your XE1 would be ZE1 squared minus RE1 squared, right? So you got that from XE1. So that's your goal here. So once you find XE1, you can also find LE1, would be magnitude of XE1 over omega, right? So that's how you get the parameter for the winding. These two parameters here for winding. Again, for the parameter for winding, we use short circuit test. For the short circuit test, we're looking for rated current, not for the rated voltage. We're going to do this problem in the class. Again, transformer performance is measured by the efficiency over here. So for the efficiency, your output power over input power, your output power depends on your apparent power times power factor time fraction of full load. So if your n could be 0 to 1, how much you're using based on the full load. Then over here, you have same thing plus all the losses, right? So n squared times copper loss plus your core loss. Core loss means iron loss in the magnetic core. So that's how you get the efficiency of the transformer. And when efficiency is 1, efficiency is 1, at the time you're basically your PC equal to PCU, right? So maximum efficiency could be 1, and at that 1, then you have the power loss equal to your core loss, copper loss equal to your core loss. And also, if you're trying to find maximum capacity of the transformer in apparent power, that would be PC over PCU times SFL. So this is the full load apparent power. Apparent power. All right. So this is the rating, max rating for the transformer. So max rating for the transformer could be found using this equation over here. Copper loss, core loss, copper loss times your full load of the transformer. And regulation, again, you have seen that regulation could be measured by in the secondary side. If you refer to everything to the secondary side, no load minus rated voltage divided by rated voltage times 100%. And if you do the refer to the primary, you can use that also, or you can use this equation. So refer to the secondary, refer to the primary here. either refer to the primary, refer to the secondary. You can use this equation as we discussed in the previous lectures. All right, that's for the transformer parameters. Now we're going to talk about the three-phase transformer. Three-phase transformer has two variations. You can connect them in delta, connect them in Y. So based on primary and secondary orientation, it could be YY. This is your YY here. This is your delta here. This is your Y delta here. This is your delta Y here. So this is the four different variation of transformer you can make because of the winding. So one thing is need to know that all those winding, they link face to face. So that means, for example here, if this is A to neutral here, that could link to AB. All right. So this one link here, I'm going to take a different color to demonstrate. Then this one, CN, could be linked to CA over here. And let's take another color here, the red one. So BN could be linked to BC here. So that means, let me show you this here. So let's say, for example, this is 100 volts, right? Over here, let's say that is same trans ratio. Then this also, this one over here, 100 volts, right? Sorry, 100 volts, not 200, 100 volts. Oh, wonderful, I lost everything. Okay, so that would be also here is 100 volts, right? Then if each of this coil has 100 volt, same 1-to-1 trans ratio, all of them will have the 100 volts, right? So what does it mean? That means over here, VAB equal to VVC equal to VCA all has the 100 volts. Take a look at that, because that's all the coil has 100 volts. Now over here, VAN equal to VVN equal to VCN equal to 100 volts, right? But VAV is line-to-line voltage for the Y connection is √3 times the line to neutral. That would be equal to VC equal to VCA. Should be equal to whatever 100 volts here times square root of 3. That will give you 171, I guess, or 73. Let me do the math here. Oh, 173. So that will be 173 volts. So in your transformer, if you don't do anything with the trans ratio, the same trans ratio here, it's still your Y connection line to line voltage is √3 times higher than delta connection line to line volt. That's a very unique thing for three-phase transformer. Again, as I said, look at this. This is one here, YY connections. It's face-to-face connection all the time. This is the delta Y connection. So this side is delta. If you look carefully here, this is all delta connection on this side over here, delta. This is delta. This is Y. And the voltage over here, Y connection is √3 times line-to-line voltage in the Y connection here, √3 times higher than line-to-line connection of the delta connection. All right. So Y connection, delta connection do not show any phase shift because they have the same voltage, because it's a face-to-face connection. But if we have Y delta or delta Y connection, there's a 30-degree phase shift. As you discussed in the previous classes, Y delta connection has a 30-degree phase shifts. And there's a factor of √3 or 1 over √3, depending on what you're measuring. Let's say if we have Y delta connection over here, this one will have √3 times of that one line-to-line connection. This side is higher. And if you go from, let's say on the other side, if you measure like that, if you measure in terms of that one over here on this side, it would be 1/3 V. Let's say is AB over here, BAB, right? So because it's the face-to-face connection, is always this face is connected to this face and so on. All right. So voltage induction happen for phase, and when you measure line to line, depending on the connection, you get root 3 times higher or 1 over square root of 3 times lower, depending on what the connection you have. So over here, that's what it's showing. If you have a Y connection on this side and delta connection on this side, depending on your voltage, you can see that there is a square root of 3 times connection between these two ends. So Y connection has the higher end here, right? And over here, the lower end has the same as line-to-line voltage and phase voltage, same thing. So that's why there's a square root of 3 times factor between Y and delta connection. And there's also a 30-degree phase shift. That's what we're talking about. All right. So Y connection transformer, always advantage line-to-line voltage is 2 to 3 times higher than line-to-line voltage of the delta connection. And you can multiply that with the trans ratio. If you have a trans ratio A, then you'll get more voltage step up. Because of that, for step up, we use delta for the primary and Y for the secondary. And step down, we use Y for the primary and delta for the secondary. I'm gonna do this class in the class. All right, that's all. Let me re-emphasize my point over here. So if you have Y and you have delta over here, okay, so A, B, C, right? So VAB on this side here, VAB on this side over here for Y is, let's do this prime over here. So that would be square root of 3 times VA prime B prime, all right? Or other way around, BA prime B prime would be 1 over square root of 3 times VAB. And we're assuming that your A trans ratio is 1. That means each of the phase over here has the same turns. So each of the phase over here, this phase and this phase the same turn and so on. So they have the same turn. If your turn is different, then it also adds to the square root of 3 values. All right, that's all for today. We're going to see you in the class.